Hi, we're here with Kim Hartmann from TenAsys, who's going to give us some more update information on issues involving multi-core processors. And Kim, we've had multi-core has been out in the world for some time, but what is your perception of how well people are actually being able to make use of the full potential of multi-core processors?
Tom, it's a really good question, and we have been on track with supporting multi-core for embedded and real-time applications for about 8 years now. And what we've seen is such a strong emphasis on using symmetrical multiprocessing or SMP operating systems to solve the use of multi-core dominate discussions to the point that people have gotten really confused with how you could take an embedded application and still get the I/O control while using a scaling, a multi-threading tool set that's designed for using an SMP scheduler. So one of the issues is dividing the platform for dedicated application is what the embedded people typically want to do. And that requires an asymmetric multiprocessing solution as compared to an SMP. And AMP solutions are maybe just haven't been advertised or promoted sufficiently to allow the customers to know that they're really capable of being able to take advantage of multi-core.
Well, do they see as the initial perception of the advantage of multi-core in trying to improve performance of a given application by multi-threading and doing SMP over it, or?
Well, therein lies the challenge is certain applications in embedded in real-time control really are not capable of being multi-threaded.
Right.
So taking advantage of this type of an architecture doesn't work for I/O controls where you've got some sort of a stimulus, input, response, and an output. It's inefficient to try to do it in a threading model where parallelism might help.
Does going to a threading model influence critical things like real-time and determinism too?
Well, it does a lot. The SMP scheduler itself is a single process dedicated on one core. So its whole purpose is to take the needs of the software side as far as what threads are in a position to run and balance them against the needs or the availability of the hardware resources and the hardware threads which are able to accept and bind to those threads and execute. So you put all the critical functionality into a scheduler that's on a single core.
So as we move toward richer embedded applications that have things like rich user interfaces and graphic displays of data and so forth, it makes sense to partition some of these functions away from the hardcore real-time functions so that you can do things that do not impact the deterministic needs of the application?
Tom, you got it exactly. If you can partition the platform for the dedicated purposes, the dedicated reasons that you want to apply the system to, then you've got half the battle taken care of already. So being able to partition and dedicate I/O is an embedded virtualization initiative. Being able to use, say, graphical user interfaces and strong HMI-based systems, such as a Windows-hosted platform, if you want to have multiple cores associated with that, that's fine. But you also need to be able to take compute resources and apply them directly to the I/O that they're going to control.
Are there inherent advantages to multi-core and virtualization in terms of security as well?
There can be, because you can isolate hardware, you can isolate processes from one another. So both in memory and CPU space, you can take advantage and provide a great deal more security in those systems.
Great. Well, thanks very much, Tim. It's been short but very informative. I thank you very much.
Thanks, Tom. As always, appreciate it.
We're supposed to